Hello everyone, we meet again to discuss part 3 of our Strand 4.2 on organic chemistry. Now today we are going to be looking at a very interesting subtopic which is alkyl halide. Alkyl halides are known as haloalkanes or halogen alkanes. In this case, we have an alkane molecule which is bonded to a halogen. Have you ever heard of anesthetics? Well, if you did, then the chemical that was used to put a person to sleep before an operation was an alkyl halide. Alkyl halide is also used in correction pen, and one of the alkyl halides that we are all familiar with is chloroform. So, we are going to be looking at the basic chemistry of alkyl halides, particularly its nomenclature, naming part, how we are going to classify them based on their structure, and we are going to look at some bonding properties and their reactions. So when we look at alkyl halide, pay attention to the general formula of the alkyl halide. CnH2n plus 1 X, where X is represented by a halide ion. It can be fluoride, chloride, bromide, or even iodide. When you name the alkyl halide, the first thing we must do is to identify the parent chain. The parent chain is the longest chain of hydrocarbons. And when we do identify the parent chain, we must start off with a carbon atom which is sticking out on the end. It can be the left, right, top, or the bottom. Keep going until you meet the last carbon in that particular chain. So once you identify your parent chain, you are going to name the branches. A branch is anything which will be attached to the parent chain apart from the hydrogens. So if your branch is a halogen, then you are going to name the branch with an O. Like if the branch is a chloride ion, then it will become chloro. Bromide will become bromo. Iodide will become iodo, etc. So let's look at one example as to how we are going to name the alkyl halide given in example 1. This kind of structure that you are given here, okay, is represented as a condensed formula. Okay, so this is a condensed formula and we are going to draw the structure of this, and then we are going to identify our parent chain and the branches. Look at the order that I am going to draw. So we have a CH3. Okay, so the first CH3 is represented here, and then we have a carbon, right, which is bonded to a Br. Now this CH3 which is in bracket cannot be in the middle. If you recall your chemistry of carbon, each carbon is bonded to 4 groups or 4 atoms. Carbon cannot have more than 4 bonds. So if the CH3 is here, that means it should have only 1 bond. This carbon should have only 1 bond. So that would become a branch. Okay, it's not really a branch, but you're going to put it right at the end. And then we have another carbon which is CH. So that's a C, and then there is a H group attached to it. There is a Br to that, okay, and we are having a CH3. So this is how we are going to expand the structure of the alkyl halide. Now once we expand the structure of the alkyl halide, we must work out what our parent chain is. So like I said earlier, your parent chain can be any carbon sticking on the side. So it can be this carbon here. You keep going, cross the carbon atoms until you come to the last carbon. So that's one possibility. I have covered 4 carbon atoms. The other one, if I start from this carbon which is also sticking to the end, I can keep going, okay, until I come to the last carbon. So that would also have 4 carbon atoms. At any point, we shouldn't change our direction. We shouldn't go like this. So once we start with one direction, you can't go back. Okay, you must continue from point A to B. So let's see which one is our longest chain of carbon atoms. Alright, so that's our longest chain of carbon atom. I have enclosed the structure. It has 4 carbon atoms. So straight after you do that, let's identify that. Single bond, 4 carbon atom, it's butane. Okay, then whatever is attached to the parent chain is your branch. So we have 3 branches in total attached to this particular parent chain. Let's name the branches. So we have a Br which is bromo, There's another Br which is bromo. There's a CH3. So one carbon is meth. If the carbon is attached as a branch, the name will end with YL. So methyl. Okay. Now we look at the numbering. Which end should you start numbering the parent chain carbon from? Should you start from the left or should you start from the right? Now, if you start from the right hand side, then we will have the Br, this Br falling on carbon 2. And these two groups will fall on carbon 3. So you have to decide which one will get a priority here. The carbon that carries more branches will obviously be given the lowest number. Another way is the carbon that has a bigger branch will also be given a smaller number. So in this case, the carbon that is here is carrying 2 branches. So that should be given a lowest number. So you start number 1 with this carbon on the left. That will be carbon 2, carbon 3, and that's carbon number 4. So now let's put all our information together. So we have 2 bromo. It will be 2 bromo, 3 bromo, isn't it? So since you have 2 same branches, you are going to use a prefix di. So it will read as 2,3-dibromo. Okay, because bromine is on carbon 2 and carbon 3. So if I say 2 bromo, 3 bromo, it is repetition. So I'm going to combine them together. 2,3-dibromo. Then you can see that there is a methyl group on carbon 2. Now you have to follow alphabetical order. B comes before M. That's why bromo is written first. Then you write the branch 2-methyl. The letter, okay, so you can see there is an alphabet O and there is a number. They are separated by a hyphen, a dash. And then you put the parent name, which is butane. So this structure is 2,3-dibromo 2-methyl butane. This is how you name alkyl halides. Let's look at example number 2. So in example number 2, again we are going to draw it first. It is very important, students, that if you are given this kind of structure and you are supposed to name them, try expanding it into a structural formula. That will make your work easier. So you will be easily able to identify your parent chain and any attached branches to that. So let me see how we do that. So we have a CH3, okay. So this is the CH3 that I have drawn. Attached to that is a carbon, okay. So we have one carbon here. That carbon has a Cl, okay, and then alright, a CH3. So this CH3 that is in the bracket will be attached to this carbon. Okay, the CH3 that's here is attached to this carbon, and then that also has a Cl group. So there we have it, and this CH3 is this one here. Now let's see what our parent chain is. Let's see if you are able to work it out. Longest chain of carbon atoms, starting from one carbon, keep going until you come to the last carbon. Okay, that's the one. So we have 3 carbons in a single bond. It's propane, and then attached to that we have 2 branches. Okay, let's see. So that's carbon 1, that's carbon 2, and that's carbon number 3. Okay, so that's a methyl group, that's a chloro group. And now when we are naming it, we will put C before M. 2-chloro, 2-methyl, and the parent will be propane. Alright everyone? So I hope you have understood how you are going to name alkyl halides now. The next thing we are going to be looking at is the classification of alkyl halides. Alkyl halides fall under 3 categories, namely primary alkyl halide, secondary alkyl halide, and tertiary alkyl halide. So let's see how these alkyl halides can be identified. Now when we're looking at a primary alkyl halide, you look at the halogen and which carbon it is attached to. So the carbon attached to that halogen should be attached to one alkyl group. When I'm talking about alkyl group, I'm talking about a carbon hydrogen group, like a CH3 group, C2H5 group, etc. Okay, so let's look at an example. Now if you look at this molecule, you can see very clearly that it is an alkyl halide. Okay, because you have an alkyl group, carbon hydrogen, and you have a halide. Now pay attention to the carbon attached This is our halide. The carbon that is attached to the halide is this one here. Now see how many other carbon atoms is this carbon attached to. So that carbon is attached to one carbon group. That's one alkyl group. Okay, the whole thing CH3 is the alkyl group. Therefore, we say it is a primary alkyl halide. Okay. Then we look at a secondary alkyl halide. In a secondary alkyl halide, the halogen is attached to the carbon which itself is attached to two alkyl group. So if you look at this example here, this is our halogen, a bromide group. Now the carbon attached to this halogen is this here. Okay. How many carbon is this carbon attached to? So that is attached to 1 and 2 alkyl groups. So therefore it is a secondary alkyl halide. Next we look at a tertiary alkyl halide where the carbon to the halogen is attached to 3 alkyl group. Okay, so if you look at this example, this is our halogen, okay, a halide ion, and that is our carbon which we are focusing on. So this carbon is attached to 1, 2 and 3 alkyl groups. Therefore, it is a tertiary alkyl halide. So students, this is how you use the technique to identify and classify the different types of alkyl halides. Okay. Now we are going to be looking at the properties of alkyl halides. So when you looked at the structure of alkyl halide, you must have guessed what type of intermolecular attraction alkyl halides have. Majority of the physical properties are due to the intermolecular attraction of a molecule. So if a molecule is polar, then it will have permanent dipole or dipole-dipole attraction. If a molecule is non-polar, then it will have temporary dipole or induced dipole. If a molecule has a hydrogen attached to a very electronegative atom, then it will have a hydrogen bonding. All three of them are weak van der Waals forces of attraction. Okay, so when we are talking about the melting and the boiling point of alkyl halides, the pattern in the boiling point of these alkyl halides reflect in the pattern of their intermolecular attraction. So basically, when we are talking about the melting point, some of the examples I have given here: chloroethane, bromoethane, chloromethane. Pay attention to the parent name. There is a ethane, there is a methane. That means they are smaller alkanes. Okay, so smaller alkanes are gases, while the alkanes which are slightly bigger than them are liquids, and those which are in gas form, they are having very weak intermolecular attraction compared to the one which exists as a liquid. Okay, so overall we can say that the intermolecular bonding that these alkyl halides have is weak van der Waals forces of attraction. We are not going to divide these weak van der Waals forces of attraction into any specific type, because some alkyl halides are polar, some of them are non-polar, depending on their symmetry. So if the alkyl halide is polar, then it will have permanent dipole. If it is non-polar, then it will have a temporary dipole. Therefore, we cannot generalize it. Okay, so we just say that they have weak van der Waals forces of attraction. Now, these weak van der Waals forces of attraction will get stronger as the alkyl halide molecules get longer and get more electrons. So when the size of the molecule increases, the strength of the bonding will also increase, which is why smaller alkyl halides will have a lower boiling point compared to the larger alkyl halides. Okay. Next one. The next property is solubility. The ability of the alkyl halides to dissolve either in water, which is a polar solvent, or in organic solvents. Now most of the organic solvents, they are non-polar in nature. Okay, so alkyl halides are very slightly soluble in water. So this explains that there are some alkyl halides which are slightly polar. So if they're slightly polar, they will be slightly soluble in water. But then there are those alkyl halides which are non-polar. That means they are not soluble in water at all, which is why they will dissolve very well in organic solvents. Organic solvents are non-polar in nature. Okay. Okay, after studying the physical properties of alkyl halide, we are now going to embark on the chemical reactivity of alkyl halide. So very quickly, very briefly, let us explain the difference between the two. When we're looking at a physical property, we are looking at those properties that can be measured easily. And a physical property can be described using intermolecular attraction. That means the bonding between the molecules. Now, when we're looking at a chemical reactivity, we are talking about the ability of a chemical to take part in a chemical reaction. So, in a chemical reaction, it is the intramolecular bonding that is going to break. Okay? Now, for a bond to break during a chemical reaction, there are two things that have to be kept in mind. It is the strength of the bond and the length of the bond. Okay? Now, for alkyl halide, the strength of the bond will actually depend on two factors. So, in short and simple, think about it this way. If the carbon and the halide bond is very strong, it will not break easily, which means it will require a lot of energy. Okay? So, do you think it will take part in a reaction very easily? Well, if it cannot break easily, that means it doesn't react well. But if the carbon and the halide bond is very weak, it will break easily, it will require less energy, and that chemical can readily take part in a chemical reaction. So let's see what are the factors which affect the strength of a bond. Number one, the electronegativity of the halogen, okay, which I will be talking about later. And number two, the bond length of the carbon to the halide. So if we look at this table here, let's compare the bond enthalpy of the different bonds between carbon and halide. If you look at carbon fluoride, it is very high bond enthalpy, which means in order for the carbon and the fluoride bond to be broken, a lot of energy is required. But if I look at carbon iodide bond, the bond enthalpy is 240 kilojoules per mole. So that is a low energy. That means carbon iodide bond is very weak, which requires less energy to be broken. Okay. Now let's talk about electronegativity. Why is carbon fluoride bond very strong? Because fluorine is a very electronegative atom. So the more electronegative atom there is, the stronger the carbon and the halide bond will be. Okay, so that basically explains the high bond energy for carbon fluoride. So carbon fluoride bond is the strongest because fluorine is the most electronegative atom compared to iodide. Then we look at the bond length. The longer the bond length is between the carbon and the halide, the weaker the bond will be. So in this case, when we're looking at the size of the atom going down the group, the atoms get bigger, okay? Therefore, the length of the bond between that atom and carbon will get longer. So, the longer the bond length is, the weaker it is and the easier it will be to break it. So, it will take part in a chemical reaction very readily. It will react very readily, okay? Well, now that we have looked at the chemical reactivity of alkyl halides and have predicted which alkyl halide is going to react quickly and which one is not, let's look at the reactions of these alkyl halides. So basically, alkyl halides undergo only two chemical reactions, and these are nucleophilic substitution and elimination. You just have to remember these two for alkyl halides. Okay? Let's look at what a nucleophilic substitution reaction is. In a nucleophilic substitution, we make use of nucleophiles. Nucleophiles are negative ions or anions, or they are molecules which carry lone pair of electrons. Any of these particles, they act as a nucleophile. Example, Cn-, OH-, CH3COO-. So you can see cyanide ion, hydroxide ion, ethanoate ion. They all are negative ions, so they are very good nucleophiles. Water, ammonia are also nucleophile because they contain lone pair of electrons on them. Now, in a nucleophilic substitution, the halogen is going to be replaced by a nucleophile. Halogen is carrying a negative charge. So if a negative charge is removed, another negative is going to replace it. The second reaction is known as elimination reaction. The word elimination simply means removal. So in this case, there will be elimination of an alkyl halide giving alkene, water and salt. So what is going to be eliminated? In an elimination reaction, the halide and one hydrogen is going to be removed. Okay? Halide and a hydrogen is going to be removed. So you will see when we look in the examples that the reactions are almost the same as nucleophilic substitution. Sometimes you will use the same reactants, but the reactions will be different. Now to prevent the nucleophilic substitution reaction from happening, the reactant we use in elimination has to be dissolved in alcohol. That is very important. Markovnikov's rule is a particular rule which is applied, okay, that will assist us to determine which hydrogen is going to be lost and where a hydrogen atom can be added. Now we are going to be looking at that in detail in a while. Okay, so let's look at a nucleophilic substitution reaction. Now in this reaction, remember we are having an alkyl halide and a nucleophile reacting together. So you should be able to identify this. So let's look at one example of an alkyl halide. So there we have it, CH3, CH2, Cl. Can you guess what is this alkyl halide called? You have two carbon atoms, that's eth group, that's ethane, and then there is a chlorine. So that's a chloroethane. Now chloroethane is reacting with OH minus. Okay, OH minus is a nucleophile because there is a negative charge. Now in this particular reaction, what is going to happen? This particular halogen is going to be removed. Now if this halogen is going to be removed, what is going to come in? The OH minus is going to come and attach itself to the carbon next to the Cl. So when that happens, we will have this CH3 remaining as it is. The CH2 will remain as it is. But in place of the Cl, we will have the OH. So what will we get? The Cl that is coming out will be an ion. So it will be Cl minus. CH3, CH2, OH. There is an OH. OH indicates alcohol. So there are two carbon atoms. Okay. And these two carbon atoms make it ethanol. You can see that this structural equation can also be represented in this pattern here. Okay, so that is nucleophilic substitution reaction number 1. Let's look at another example here now. So this time we are again using chloroethane. So chloroethane is reacting with a different nucleophile. This time it is reacting with ammonia. Now can you explain why ammonia is a nucleophile here? Because it carries a lone pair of electron. Okay, so let's just try to talk about the chemistry of atoms here a bit. Carbon is in group 4, therefore it should always have 4 bond. Nitrogen is in group 5, it requires 3 electrons. So nitrogen will form 3 bond, no more than that. You can see ammonia has 3 bond already. Okay, so when the reaction is going to take place, this particular group is going to remain the same. Nothing is going to happen to them. The only change that is happening is this halide here. Okay, otherwise the rest of the parent chain is remaining the same. So the CH3, CH2 remains the same. The Cl is going to be removed, and in place of that, the ammonia group is going to come in. Remember, the nitrogen is coming with the hydrogen. Now think about it. The nitrogen is already having 3 bond. We said nitrogen has only 3 bond, isn't it? Because it requires 3 electrons. So if this particular group attaches itself to the carbon, then it will end up forming 4 bond, which is not possible. So it will not be attached as NH3, but it will be attached as NH2. So that nitrogen can have 3 bond only. 2 from the hydrogen and 1 bond here. So what will happen to the rest of the molecules? Now you can see there are 2 ammonia molecules. Okay. 1 ammonia is still remaining. Out of the 2, 1 ammonia still remains. And the other ammonia has a hydrogen remaining. So what will form? It will form ammonium ion NH4 plus, and the Cl minus that is coming out will attach itself. So plus and minus will give you ammonium chloride. Okay, so you can see that now we have a new chemical compound here which is called an amine. And alkyl halide will give you an amine. Amine is those compound which has a carbon, hydrogen and a nitrogen. Okay. And then you can also represent the structure like this. Let's look at other examples of nucleophilic substitution. So we look at chloroethane again, but this time we have a Cn minus. Okay, reaction will be the same. CH3, CH2 will remain the same. The only changes that will happen is to the chlorine here. So that chlorine is removing. In place of the chlorine, the Cn minus is coming. Okay, so carbon is in group 4, so requires only how many electrons? 4, isn't it? Nitrogen is also there. Nitrogen should have how many bonds? 3 bonds. So 1, 2, 3 bonds. And then this carbon will be bonded to something else here. So carbon will have a total of 4 and nitrogen will have 3 bonds. So there you have it. Okay. And then what is coming out is chloride. This particular compound is called a nitrile. A nitrile is those compound which has a carbon hydrogen group, alkyl group, and a Cn. And then you can represent the entire equation in a condensed formula like this here. And the last example. So we have chloroethane, this time reacting with CH3O minus. CH3O minus is called a methoxy group. Okay, it's called a methoxy group. Now when the reaction takes place, parent will remain the same. Okay, chloride is going to be removed, and you can see that methoxy is a methoxy because there is a carbon, one carbon, and there is an oxide. So methoxy group. So this carbon will be bringing hydrogen and oxygen with it and attaching itself in place of chloride. So now we will have, okay, let's see how the attachment is going to happen. Carbon, hydrogen, oxygen. Which of these three? It is the oxygen that's negative, isn't it? So when one negative goes, another negative should come in. So the orientation will be that it is the O which will come and attach here. And then the CH3 will be pointing away. So O will be attaching itself and the CH3 will be away. So you have created an ether. An ether is an organic compound where O is in the center and you have 2 alkyl group on the side. Right? And then you can see the condensed structural equation. So students, there we have it. I hope you have understood what nucleophilic substitution reaction is. Nucleophilic means nucleophile. Substitution means nucleophile is substituting. Okay. So after looking at a nucleophilic substitution, we are now going to look at the last reaction of alkyl halide, which is elimination. You must pay attention to the keywords. When we're looking at a nucleophilic substitution, it simply means a nucleophile substituting, means replacing. When we're looking at elimination, we are talking about a removal of some particle. Okay, so in an elimination reaction, make a note that there will be removal of a halogen and one hydrogen. So let's look at an alkyl halide here. Okay, so you can see I'm expanding the structure here, unlike the previous one which we did. Okay, so we have any guesses as to what this compound is? Well, this compound is 1, 2, 3, 4. There's a butane group here. So that's 2-chlorobutane. Okay, that's a 2-chlorobutane alkyl halide. Now it's reacting with KOH. If you leave this reaction as it is, it will undergo a nucleophilic substitution, because in KOH, OH minus is a nucleophile. So if you do not add alcohol to this reaction, then the OH minus will substitute the Cl. Okay, therefore, to prevent nucleophilic substitution from happening, this is what is required. Heat the reaction with alcoholic potassium hydroxide. That's very important. Once that is done, then nucleophilic substitution will not happen, but elimination will happen. Okay, so now in elimination, let's remove first of all the halide. Okay, now there is a deciding factor. Which hydrogen is going to be removed? The hydrogen that is going to be removed will be coming from a neighboring carbon, not from the same carbon. It must come from the neighboring carbon. So this particular carbon here has two carbon neighbors. We have one here and we have another one here. Okay, so we need to decide which of these, okay, is going to lose the hydrogen. So this particular carbon is having 1, 2, 3 hydrogens, and the other carbon, okay, with the arrow there, is having 1 and 2 hydrogens only. Okay, this group is a carbon hydrogen, this methyl group, this is not hydrogen. So you have to look at which carbon is having less hydrogen, and that is where Markovnikov's rule comes in. Let's read this rule and understand. It states that in an addition reaction of the molecule, the hydrogen atom of the attacking molecule will attach to the carbon which has more hydrogen atom. Now, if you are adding a hydrogen atom, the hydrogen will be going to the carbon that already has more hydrogen. But if you are eliminating something, removing the hydrogen, like in this reaction here, the hydrogen will be removed from the carbon that has less number of hydrogen atom. So very short and simple, the rich carbon will get richer when it is added. The poor carbon will get poorer when elimination happens. So now we have carbon A and carbon B here. Which carbon do you think is going to lose the hydrogen? It is the second carbon, this one here. This carbon is going to lose the hydrogen because it has less hydrogen atom. Okay, so let's see. The halide is removing and the hydrogen is removing. Okay, the neighboring hydrogen, remember that. So after the halide and the hydrogen is removed, we are left with a CH3. Okay, so this whole of this is the CH3 that's left there. We have the carbon, which is this carbon here. Attached to that is the hydrogen, and then we have this carbon here which has the hydrogen on top, and we have a double bond. Now do you understand why there is a double bond? Okay, because 1, 2, 3, 4 bond has to be created between carbon atoms, and then we have the CH3. So in elimination reaction, an alkene is produced. Now let's look at the byproduct. What elements are coming out? The OH, okay, is now going to pick on the H that has come out. So together they will form water. And you are now left with K and Cl. So the K and the Cl will combine with each other to form KCl. So in an elimination reaction, there will be 3 products: alkene, water, and the salt. Okay, and this particular alkene is called but2-ene. You can even write it in a condensed structural formula as shown here. Alright, so I hope you have understood about the difference between nucleophilic substitution reaction and an elimination reaction. So this is the end of alkyl halide. I hope you have understood everything that I have said in this particular video. If you have any questions or any queries, do let me know. Okay, go back to this video, watch it over and over again so that you are able to answer the questions that are given in your notes. In the next video, we are going to be discussing about the next organic compound, which is amines. Until then, students, take care, keep studying, keep recapping your notes, and bye.